Hello friend, in this video we will see what is meant by subspace, few examples of subspace and theorems of subspace. So first of all, subspace is a subset of a vector space, non-empty subset of a vector space if under the operation of V the subset satisfies the properties of vector space, then it is called as a subspace of a vector space. Let V be a vector space over a field F. Suppose U is non-empty subset of V if under the operation of V U satisfies conditions of vector space, then U is subspace. We know that V is a subset of itself, that is V is subset of V. Also, if we take U equal to the set consisting of 0, then both are the trivial examples of a vector space. Now we prove theorem of a vector space. A non-empty set, let me write theorem, a non-empty set U of a vector space over F is a subspace of V if and only if first condition U1 plus U2 belongs to V and second condition alpha U belongs to U, U1 plus U2 belongs to U. So if these two conditions are satisfied, then U is a vector space. This is our theorem. A non-empty set U of a vector space V over F is a subspace of V if and only if U1 plus U2 belongs to U and alpha U belongs to U. So let us prove this. Proof: first assume that U is subspace. U is a subspace and therefore it satisfies all the conditions of vector space, that is closed under the operation addition, and therefore if we take any two element U1 and U2, U1 plus U2 belongs to U. Now second condition is obvious by the definition of vector space, alpha U belongs to U. So both conditions are satisfied when U is a subspace. Now let us see the converse of this theorem. Conversely, we assume U is subset, U is a non-empty subset, U is non-empty subset satisfies both conditions 1 and 2. It satisfies these two conditions. Now we see that according to the first condition, alpha u belongs to V by first condition, and by second condition we have alpha u belongs to U, therefore alpha u plus V belongs to U. This is by combination of the two conditions. First condition shows that alpha u belongs to U. Second condition shows that if we have two member, let us, that means this U, this is alpha u is one member and V is another member, so their addition belongs to U. So this combination of two conditions shows that alpha u plus V belongs to U. Now plus is a commutative operation, therefore we write alpha u plus V equal to V plus alpha u, and it is also belongs to U. If we take alpha equal to minus 1, so we have V minus U belongs to U, and this shows that U is a abelian group. This is a property of a group with operation plus. When this combined condition satisfies, it is called as a abelian group. We have shown that plus operation is a commutative, and therefore V minus U belongs to U by that condition. In this above conditions we have taken alpha equal to minus 1. This is satisfies for any value of alpha. Hence if we take alpha equal to minus 1, V minus U belongs to U. Okay, now consider any two element. If we take two element, let me take two element first. Suppose that U comma V belongs to U. Since U is a subset of V, we have U comma V belongs to V, but V is a subspace, and therefore it satisfies these conditions alpha into U plus V equal to alpha U plus alpha V. Second conditions, alpha plus beta into V equal to alpha V plus beta V. Third condition is alpha times beta V equal to alpha beta V. And fourth one, this is obvious condition of vector space. Since V is a subset of U, U comma V belongs to V, therefore they are member of V, and for these two member, these conditions are satisfied in V, and therefore they are satisfied in U, and hence U is a vector space. So we have proved that if a non-empty subset U of a vector space V over F is a subspace if and only if these two conditions are satisfied. Now I am clearing the screen. Let me clear the screen. Then we will prove one example: intersection of two subspaces. Intersection of two subspaces is a subspace. That is, consider that problem. Suppose I have two subspaces. So problem is intersection of two subspaces. If we have two subspace, let us take their intersection. Then if these are the intersection of two subspaces of a vector space V over F is a subspace. So let us solve this. Solution. First we suppose let u comma w be two subspaces of vector space V. Now what we have to show? We have to show that their intersection, we have to show that u intersection w is subspace. This is our problem. Now we have taken these are the two subspaces. Two subspace means both contains additive identity, that is 0 belongs to u, 0 belongs to w. This means that 0 is a common element and hence 0 belongs to u intersection w. This shows that this set is a non-empty. Now consider that any two element belongs to u intersection w. This implies that u comma v belongs to u and u comma v belongs to w. Now for any alpha comma beta belongs to f, u and v are the subspaces. Therefore alpha u plus beta v belongs to u and alpha u plus beta v belongs to w. So this is a common element, alpha u beta v. Therefore alpha u plus beta v belongs to u intersection w. So this shows that this is an alternative definition of a vector space. When alpha u plus beta v belongs to v, it satisfies, which says that it is also a subspace. Here for any two element u comma v belongs to u intersection w, this condition is satisfied and hence intersection of two subspaces of a vector space over F is a subspace. So this is about two subspaces. Now question arises in mind, can I take three subspaces, four subspaces or any set of subspaces? So we will prove the intersection of subspaces is also, any ordered set is also a subspace. First I will clear this, clear the screen. Okay, so we are going to prove another problem. Problem is if we have a set of subspaces, S lambda, small lambda and capital lambda is ordered set. So these are the subspaces, these are subspaces of V. Now the question is whether their intersection S lambda belongs to capital lambda is ordered set, is a subspace. This is our question. Intersection of subspaces, any finite, any ordered set. So we prove this is also a vector space. Let us solve this. Solution: suppose S equal to intersection of S lambda such that lambda belongs to capital lambda. Now we see that all are subspaces. S lambda are subspaces. These are the subspaces, therefore 0 belongs to S lambda for all lambda belongs to capital lambda. So 0 is a common element and therefore 0 belongs to S, and this shows that S is non-empty. Now consider any two element of S, u comma v belongs to S. This implies that u comma v belongs to S lambda for each lambda. It is they are member of every set S lambda, but S lambdas subspaces, and therefore if we take scalars alpha comma beta belongs to F, alpha u plus beta v belongs to S lambda for each lambda. Look at this. This is a member of alpha u plus beta v belongs to S lambda for every lambda. It belongs to every lambda, therefore it belongs to intersection. This shows that alpha u plus beta v belongs to intersection of S lambda for lambda belongs to capital lambda, and this is a nothing but S, and therefore intersection of subspaces is also a subspace. We have proved one theorem and one example of subspace.